Hello everyone, this is Dr. Webb, and welcome to the next abstract algebra video. So in this video we're going to start talking about a topic that we've kind of danced around throughout the term, but now we're going to lay down some very specific definitions about what we're talking about. And this all revolves around isomorphisms, or when groups are isomorphic to each other. So what's the definition of isomorphism? Well, so let's let G and G prime be groups, and let's let phi be a function from G to G prime. Then we're going to say that phi is an isomorphism if one, phi is one-to-one and onto, and so phi is a bijection between the two groups. And secondly, if phi plays around well with the group operations. And so what we mean specifically is that if we have any two elements A and B and G, then phi of the product of A and B is equal to the product of phi of A and phi of B. So the important thing to notice about this second part of the definition is that on the left-hand side, for A and B, we're using the group operation of G. So this is G's group operation. However, on the right-hand side, when we're taking the product after we apply the map, over here we're using G prime's group operation. And so you can kind of think about phi takes the group operation in G and it transforms nicely into the group operation in G prime. Okay. And so if there is an isomorphism between two groups, G and G prime, and in general between two random groups, there's not going to be an isomorphism between it. Isomorphisms are very special. But if there does exist an isomorphism between G and G prime, then we're going to say that the two groups are isomorphic. So the isomorphism is the map between G and G prime. Isomorphic is talking about two groups that have an isomorphism between them. So isomorphic is talking about a relationship between groups. Isomorphism is talking about the map between them. So let's start off with a quick example. So we're going to have G be this cyclic group of 4 cycles generated by the 4 cycle 1, 2, 3, 4. And so it has the identity 1, 2, 3, 4, 1, 3, 2, 4, and 1, 4, 3, 2. And of course, the operation for G here, this is functional composition. Composition of permutations. Of permutations. And our G prime is going to be a subset of the complex numbers with multiplication, the subset 1, I, minus 1, and minus I. And so the group operation here is multiplication. And we're going to define phi to be very explicit. So phi is going to send the identity in G to 1 in G prime. It's going to send the 4 cycle 1, 2, 3, 4 to I. It's going to send 1, 3, and 2, 4 to minus 1, and 1, 4, 3, 2 to minus I. And so we can see, since this is a map between two groups, both of order 4, and the way we've written it, this right here is showing that it's one-to-one and onto. So by definition, by the way we've defined phi, phi is one-to-one and onto. So the only thing really to check is that it's playing around well with the group operations. And so we can just play around some with that. And so if we did phi of, let's say 1, 2, 3, 4, and 1, 3, 2, 4, well, does this equal, well, this should be phi of 1, 2, 3, 4, and phi of 1, 3, 2, 4. Okay, so let's check. So 1, 2, 3, 4 applied to 1, 3, 2, 4. So 1 goes to 3 goes to 4. 4 goes to 2, which goes to 3. And 3 goes to 1, which goes to 2. So we get 1, 4, 3, 2. And 1, 4, 3, 2, this is equal to minus I. And we can think about minus I as being I times minus 1. And I is phi of 1, 2, 3, 4. And minus 1 is phi of 1, 3, 2, 4. Okay, and so this is just one example, but we could go through all the possible combinations and you would see that it works. And so in the way that we've talked about that two groups are isomorphic before, it's been relating to that they have identical Cayley tables. And that having identical Cayley tables, that's the same. That encapsulates this definition of isomorphism because, well, one-to-one and onto, that's really coming from they have to be the same size table. And then the entries have to be the same. Well, what's in the entries? Products between elements. And so if what you have and all the entries inside the Cayley tables are the same, that's saying that how you do the group operations between the two groups gives you the same outputs. Okay, and so isomorphism at the end, especially for finite groups, isomorphic, this is corresponding to Cayley tables agree with each other. Okay, and so if we did the whole Cayley table for this group of permutations, we get something that looks like the Cayley table for 1i minus 1 and minus I. Okay, so let's talk about some basic properties of isomorphisms. So phi is an isomorphism from a group G onto a group G prime. So remember, phi is a bijection. It's one-to-one and onto, and it plays well with the group operation. Well, then first, phi is going to send the identity of G to the identity of G prime. So let's let E is going to be the identity of G. And let's let E prime, this is the identity of G prime. Okay, so then for any G in G, we have phi of the identity times G. Well, on the one hand, this is just equal to phi of G, because the identity times G is just G. On the other hand, this is going to equal phi of the identity times the phi of G, and so this is using the rule for the group operations, that the group operations play around with each other. So phi of the identity times phi of G is equal to phi of G, and then we can cancel off the phi of G's, and we end up with phi of E is equal to the identity of G prime. Okay, and so this right here, this is just using cancellation between these two objects, cancellation happening in G prime. Okay, and so this gets us our result. Secondly, for every integer n, and for every group element A in G, phi of A to the n is equal to phi of A raised to the nth power. Okay, or whatever that means, phi of A applied to itself n times in terms of the group operation of G prime. Okay, so first let's prove this for positive integers. So if n is greater than 0, well then phi of A to the n is equal to phi of A applied to itself n times, And so then using the fact that phi plays well with the group operation, we can write this as phi of A times phi of A out to phi of A, and this is done n times, and that's equal to phi of A applied to itself n times. Okay, and so that there it is for positive n. So now we need to think about what happens for negative n. So the case that n equals 0, that's the identity case, which we already did. And so to think about negative n, really I'm going to start with just proving that phi of A inverse is equal to the inverse of phi of A. And so proof of this is that if I do phi of A times phi of A inverse, on the one hand, this is equal to phi of the identity in G, which we just proved is equal to the identity in G prime. But we also have that it's equal to phi of A times phi of A inverse. And so if they multiply together to be the identity in G prime, this happens if and only if phi of A inverse equals the inverse of phi of A. Okay, so then the inverses play well with each other. Now, if n is negative, then we can think about phi of A to the n as equaling phi of A inverse raised to the negative n. And so phi of A inverse raised to the negative n. Now negative n, if n is negative, now negative n is positive. And so we saw that this is equal to phi of A inverse raised to the negative n. And then we just proved that phi of A inverse is equal to phi of A inverse. And then that's being raised to the negative n. And so it's the same as, that's the definition of phi of A to the n when n's negative. Okay, so phi plays around well with applying an element to itself a number of times. Okay, for any elements A and B and G, A and B commute in G if and only if phi of A and phi of B commute in G prime. Right, so proof for this, A and B commute, should be another M there, if and only if AB equals BA, and this will happen if and only if phi of AB is equal to phi of BA, and phi of AB, using our rule for compositions, is going to equal phi of B times phi of A. And so this means phi of A and phi of B commute. And all of these implications work both ways. So this is a case where we can do if and only if in one step. Okay, if G is a cyclic group generated by A, if and only if G prime is a cyclic group generated by phi of A. Okay, so let's start proving this. Let's let G be generated by A, and let's let G prime be some element of the group G prime. Then that means that there exists some G in G such that phi of G equals G prime, and this is because phi is a bijection. So since it's a bijection, it's onto. That means that for anything in G prime, there's some preimage of it. There's some element that gets sent to it in G. And then this means that G is equal to a to the n for some n in the integers, because G, the group G, is cyclic. And so then you have that G prime is equal to phi of G, which is equal to phi of a to the n, and so then it's equal to phi of a raised to the nth power. And so since this is true for any element of G prime, this means that G prime is cyclic, generated by phi of a. Okay, and so this is the forward direction. Now in the reverse direction, pretty much all that we would need to do is pretty much swap all of our G's and G primes all the way along, right? And so let's do that quickly. So if G prime is cyclic, generated by phi of a, then for any G in G, we have that phi of G, which is now in G prime, is going to equal to phi of a raised to the n in some, for some integer n. And so then we have that phi of G is equal to phi of a of n, and then we can pull the n on the inside using the other direction of what we proved with powers. And so then by one-to-oneness, so since phi is 1-to-1, we have that G has to equal a to the n, because they're equal to each other once we plug them into phi. And so then this finishes the proof for the other direction. So G, anything in G can be written as a power of a. So G is generated by a. Okay, number 5. The order of A is equal to phi of A for all A and G. And so proof of this, so let's assume that they, if they are infinite, so the order of A is infinite if and only if a to the n is equal to the identity implies n's equal to 0. So that's my statement. And then this is true. This would imply that phi of a to the n is equal to the identity in G. Implies n's equal to 0. And so then that means that the order of phi of a is infinite as well. So now let's do the finite case. So let's let a be less than infinity. And so in particular, let's let a have order n. And so then that means that phi of A raised to the nth power, on the one hand, this is going to be the identity in G, because A to the n is the identity in G. So phi of A to the n is going to be the identity in G prime. On the other hand, it's equal to phi of A raised to the nth power. And so then that implies that the order of A is greater than or equal to the order of phi of A. Now going the other direction, let's let the order of phi of A equal k. And so that means that phi of A raised to the k is equal to the identity in G prime, which means that phi of, we can pull the power to the inside, is equal to E prime, and this means that A to the k is equal to the identity in E, and this gives us that the order of phi of A is greater than or equal to the order of A, and then since the orders are both greater than or equal to the other one, the only possibility is that they're equal. So the orders are equal. Number 6, for a fixed integer k and a fixed group element b in G, the equation x to the k has the same number of solutions in G as does the equation x to the k equal phi of b in G prime. Okay, so this one's a little bit technical. It's similar to the order question, slightly different, but the idea is basically exactly the same. And so the idea is we're just going to be kind of counting solutions. And so on the one hand, if G is a solution to x to the k equals b in G, then that means that G to the k equals b, and then that happens if and only if phi of G to the k, which is equal to phi of G to the k on the inside now, and that's going to equal phi of b. And so we've gotten that phi of G is a solution to x to the k equals phi of b in G prime. Okay, and so the solutions are mapped to each other, right? And so then if the solutions are mapped to each other, well, on the one hand, if there's infinite solutions on one side, that has to mean that there's infinite solutions on the other side because of the one-to-oneness and on-to-ness. On the other hand, if there's only a finite solution, let's say that solution is n, so we have n different solutions in G, well then phi is going to map n different solutions to n different solutions in G prime. And so again, by the bijection, that means that the number on each side is the same. So since phi is a bijection, number of solutions in G equals number of solutions in G prime. And that's just because we've just shown that a solution in one maps to a solution in the other, and so the bijection says that we have the same count the whole time. Okay, the last one, if G is finite, then G and G prime have exactly the same number of elements of every order, right? So if G is finite, then all of its elements have finite order. And so then we can do sort of a set theory counting argument to finish this off. And so the way to think about this is that the number of else in G with order n, well, this is equal to the number of solutions to x to the k equals the identity in G minus, so we have to take out all the solutions where the order is smaller than that, and so if that means that we'd have to take out all of the, should be x to the n, let me fix that, should be x to the n there, so we need to take out the number of solutions to x to the d equals e for all d that divide n and d is strictly less than n. Right? And so, right, if we're looking for the elements of order e, of order n, well, that means that x to the n is equal to the identity, but it also means that that for any power smaller than n, we're not going to have the identity, and so the only way it could have a smaller order is if its order actually divided n. That's based on what we've proved before about order of elements in groups. And so then this draws back to the last property that we proved, saying that the number of solutions to each of these sets is all going to be equal. And so this is equal to number of solutions to x to the n equals e prime in G minus number of solutions, this is in G prime, to x to the d equals e for any d that divides n, d less than n. This should be an e prime, and then that's equal to the number of else elements in G prime of order n. And so this is a rough set counting argument. I didn't write them properly as sets, partially because of space, but I think the idea is there, right? That if you want to count the number of elements in G with order n, well, then that's the number of solutions to x to the n equals the identity in G, but then you have to subtract off if the order was actually smaller than n. The only way the small order could be smaller than n is if the order divided n, and so we have to take off all of the number of solutions of x to the d equals the identity for any d that divides n and is strictly less than n. And then that argument goes through the same way to count the number of elements in G prime of order n. Okay, so those properties were a mouthful. Now, based on these properties, we can then conclude that there's some more properties. I'm not going to spend as much time writing out full proofs for these because the ideas were already developed in the previous proofs and proving the previous properties. But so now, again, suppose that phi of G is an isomorphism from G to G prime. Well, then phi inverse is an isomorphism back from G prime onto G. And so this just has to go that since phi is a bijection, it has an inverse. And so since phi obeys this this law, this rule plays well with the two group operations, then the inverse is going to as well. There's not really much to prove there. G is abelian if and only if G prime is abelian. So this, we can see this is pretty quickly true because A and B commute in G if and only if phi of A commutes with phi of B and G prime. That was one of the properties we proved. And so abelian just means that that's always true for any A and B and G. So that just really adds one line at the beginning and one line at the end for that proof. G is cyclic if and only if G prime is cyclic. So we already proved that if G is generated by A, if and only if G prime is generated by phi of A. And so this is just a direct consequence of that. If K is a subgroup of G, then phi of K is going to be a subgroup of G prime. So this we can do quickly with the subgroup, with the one-step subgroup test, right? And so then if we have that, let's let A and B be elements of phi of K, then that means that there exists, let's say A prime and B prime are in phi of A. Then there exists an A and B in K such that phi of A equals A prime and phi of B equals B prime, and this is by the definition of phi of K. And since these A and B are in K, which is in a group, then this means that AB inverse is in K. Because B inverse has to be in K, and then it's closed. And so this means that phi of AB inverse is in K. And so then this means that phi of AB inverse is in phi of K, and this is equal to phi of AB inverse by using the group properties that we've used, using the properties of isomorphisms. This is equal to A times B prime inverse, right? Because phi of A is equal to A prime, B, phi of B is equal to B prime, and so then that means that phi of B inverse is equal to B prime inverse. Okay, so that's the one-step subgroup test, finishing that off for us. Now, we also can do this the opposite way, that if we start off with K prime being a subgroup in G prime, then the preimage of K prime, this should be not K over bar, that should be K prime there, little typo, sorry, is a subgroup of G, and this is actually just the same statement as the other one, just applying phi inverse instead of phi. So the fact that phi inverse is also an isomorphism gives us this. And last but not least, the center of G, the image of the center of G is going to be the center of G prime. And this is just, again, similar to talking about G being a billion if and only if G prime is a billion. So A commutes with everything in G if and only if phi of A commutes with everything in G prime. And that's straightforward from the properties that we proved before, from the fact that A and B commute if and only if phi of A and phi of B commute in G prime. So I know that there were a lot of properties that we went through in this video. We are done with them now. In the next videos, we will actually be looking deeper at isomorphisms. And so I will see you again soon to talk about those.